Welcome back. So we continue looking at the solution of this full flapping equation, and as we have said, the solution could be expressed can be expressed as a Fourier series expression, which would have constant term, cosine term, and sine term. And we discussed about the effect of the cosine term. Now, similarly, the sine term, I mean, we can have the positive sign constant means that the blade which is rising tends to be bent downwind when horizontal. When descending, the blade goes upwind. So overall, the plane described by the tip would tilt to the left in the direction of positive yaw. So which has been shown in this figure. So that means you can also have positive sign constant, which would mean the blade when it rising tends to be, rising tends to bend downward when horizontal. And when descending, the blade goes upward. So you can see that that makes a plane like this, what is shown in this figure for the sine term. So we can summarize one, the constant term theta 0 that indicates that the blade bends downward by a constant amount as it rotates. So as in coning. Beta 1c, say that indicates that the plane of rotation tilts downwind when the blade is pointing down and upwind when pointing up. And beta 1s indicates that the plane of rotation tilts downwind when the blade is rising, upwind when descending. Okay. So this is what you have in summary of that particular solution to the full flapping equation, where beta 0, which is the Kuning term that indicates that blade, blade bends downward by a constant amount as it rotates. Beta 1c indicates that the plane of rotation tilts downwind when the blade is pointing down and upwind when pointing up. And beta 1s indicates that the plane of rotation tilts downward when the blade is rising and upwind when descending. So this is in summary. We have uh, different terms which are so now these constants are functions of the various parameters in the model. So the coding term is related primarily to the axial flow, blade weight, and spring constant. So if you see the coding term, that is related to axial flow, blade weight, and the spring constant. Okay. The sine and cosine terms depend on, so the sine and cosine terms, they depend on yaw rate, okay, wind shear, crosswind, which is yaw error, and as well as the same terms that affect coning, plus terms that affect coning as well. Okay. So now we apply assumption that the flapping angle can be expressed as this beta naught. So the beta naught would be uh, plus beta would be beta naught plus beta 1c cos psi sin psi. So this once we using this, then we can possibly using this we can possibly have solution in closed form. So one can take derivative to this particular equation and substitute the results into the full bending flapping equation, and then collecting the terms to match coefficients of the function of azimuth. So what we get, finally what we have is a matrix K B minus gamma q bar d bar 2b K minus 1 gamma by 8 gamma u naught by 6 gamma by 8 K minus 1, where beta naught, beta 1c, beta 1s equals to, you have gamma by 2a minus 2q bar minus gamma by 2 b naught A3 KNUS U bar by 4. Then we have minus gamma by 8 Q bar. So we get a matrix for this. So now this is more like an again a generic form of the solution. So what we are doing, once we say that the beta can be expressed in terms of this beta naught, beta 1c and beta 1s, and then take the derivative and put it in the full flapping equation that we have here. So collecting the term and the coefficients, match the coefficient, then we can get this system, which is a generic in nature. Now we can have solution of the flapping equation for different. Now we can obtain the simple solutions. So simple solutions. So now we can either we can use this is a matrix, can use a Cramer's rule, find out. Then the approach will in fact be taken in as it is. I mean, it's an simple linear system, so one can find out multiple ways this solution. But uh, so this is not a big task as such. But what would be more interesting to see the effect of different terms. Okay, once we consider and how the turbine respond to that, or rather the dynamic response of the turbine with respect to those terms would be pretty interesting to see. So, which kind of it's like an we want to see the dynamic response of a turbine to a fairly simple inputs even without considering the effects of turbulence and nonlinear aerodynamics. So that would be something interesting to see. So what we can do, we can go a little bit of case by case basis. And so let's say first we say that rotation only situation. Uh, so we are considering rotation here, but what we have gravity is 0, crosswind effect is 0, yaw rate is 0, offset is 0, hinge spring is 0. So it's only rotation only considered. Okay, and rest of the terms here are considered to be 0. So then the equation, this matrix, so these equations I would say the it becomes only 1 0 0 0 0 gamma by 8 0 minus gamma by 8 0 beta naught gamma by 2a 0 0. So the solution to this is pretty straightforward. So what we get, beta naught equals to gamma by 2a. There is only coning in this case. So only cooling in this case. Uh, I mean, what happens is that there is a balance between aerodynamic thrust and the centrifugal force, which determines the flapping angle. So balance between aerodynamic thrust and centrifugal force determines the flapping angle. So there is no dependence on azimuth. So this is probably the simplest of the, I mean, so that's what I said it would be interesting to look at the impact of different terms in the final solution. So if you only consider rotation, this gives you the cooling effect only, and the other centrifugal force and aerodynamic force balance between each other. So the which determines the flapping angles, and there is no dependency of the azimuth. So that is one of the simplest situation that one can have. The second one, what we can consider is we will keep rotation, then we add hinge spring plus offset. Okay, so that is what we will add to that. Now adding the spring and offset terms give the same form of the solution. So adding the spring and offset terms give same form for the solution. So flapping angle is, however, the flapping angle is reduced. So the star becomes K 0 0 0 K minus 1 gamma by 8 0 minus gamma by 8. So gamma by 2a 0 0. Okay. So the solution here is beta naught is gamma a by 2k. So the cooling angles now results from a balance between the aerodynamics moment on the one hand and the centrifugal force and the hinge spring moments opposing them. So as one can expect that stiffer the spring, the smaller the cooling angle. Okay. So this tells that stiffer the spring, smaller the cooling angle. So essentially, that's what you get from this particular situation where you have this balancing act between aerodynamics moment and the centrifugal force, and the other side is the hinge spin moments, which would oppose to that those two moments. Now we can include some more term here. Now we can include rotation plus hinge spring plus offset plus gravity. Obviously, when we add gravity, it will. So if you see that what we are doing, essentially, once we get this matrix, we're trying to see the impact of different terms and the components on the final solution. So what is happening is that uh, rotation gives you coning only. Then once you add rotation to hinge spring and offset, that also give you coning, but there is an effect of the hinge spring moment and which balances out the aerodynamic moment and the centrifugal moment, and then that you get to see stiffer the more stiffer spring you have, then smaller the coning. Now we want to include gravity, but once you include gravity, it complicates the solution. So that we will discuss in the next session. Thank you.